I would like to talk about ways of depicting organic structures in organic chemistry. And I'm going to be focusing on three types of structures. One of them is the Lewis structure, and hopefully you are all are familiar with that by now. But you can take Lewis structures and convert them into what are called condensed structural formulas, which is shown on this table. And we'll also talk about what is called a line angle formula. Before we get into that, I want to draw your attention to different types of groups that we encounter in organic chemistry. And this will make life a lot easier if we learn some of these groups before we try to draw condensed structural formulas. And some of the groups are shown over here on the left. You can see there's a methyl group, which is a CH3. And this does not stand by itself, but is part of a larger structure. So something else is bonded to that methyl group. There are 4 bonds to carbon. 3 of those bonds are to hydrogen. So that's the methyl group. There's also a CH2 group, which is the methylene. And then if you have just one hydrogen, that's called the methine. And then we have some heteroatoms that we're going to encounter. This would be anything but carbon and hydrogen. For example, oxygen, nitrogen, halogen, maybe sulfur, something like that. So that's going to be a heteroatom, and sometimes we have groups here that we can identify like hydroxyl group, which is part of an alcohol, for example, and NH or NH2, which is a part of an amino group or an amine. And then we also have an ether, which is an oxygen that typically bridges 2 carbons in a structure. So let's take a look at some of these structures. Here we have ethane. Now what is ethane? Ethane is 2 carbons. It's a hydrocarbon and it has 6 hydrogens. So there are all single bonds in ethane here. It's C2H6. And you can see the Lewis structure here, but what you should be able to do is recognize some of these groups over here on the left side. So in this case you'll see that you can draw in the red square there the methyl group. That's a CH3. And on the right side, there's another CH3. And we can think about that as 2 methyl groups that are bonded together. And then we have a condensed structural formula shown like this, CH3, CH3. Let's take a look at something called isobutane, which is a branched hydrocarbon. And you can see, first of all, that there's a methine in green here. You can see that CH right there. And you have 1 hydrogen bonded to that carbon. And then how many methyl groups are present in that molecule? And you can see that there's actually 3 methyl groups bonded to that methine. And so then we have CH3 with parentheses around that CH3. That means it's taken 3 times. So I have 3 methyl groups that are all bonded into that methine group. So there's a condensed structural formula for isobutane. If we take a look at hexane, hexane is a 6 carbon chain of groups, and you can see that there's 2 methyl groups, methyl group on the left side and 1 on the right side, so you can see those. And then there's 4 CH2s or methylene groups, and we can abbreviate that. We could string them all out, or we could just write CH2 parentheses 4 times, and we end up with a condensed structural formula again. What about heteroatoms? Here's diethyl ether. Let me point out here, there's a group called an ethyl, which I didn't show on the left over here, but it's actually got a CH2 and a CH3 together, and that's an ethyl group right here. And you can see this is called diethyl ether. There's 2 of these ethyl groups over here, 1 on the left and 1 on the right. How would we write this? Well, we would show a CH3, that's a methyl, bonded to a CH2, and then an oxygen bridge, another CH2, and another CH3. And then we can take a look at ethanol. Ethanol has an ethyl group, which is a CH3, and a CH2, which is bonded to a hydroxyl group. Notice in the condensed structural formulas, you don't show the lone pairs necessarily. All right, so in isopropyl alcohol, you may know that as rubbing alcohol in your medicine cabinet to keep you safe against COVID-19. This has 2 methyl groups, taken twice, and then a methine with a hydroxyl group bonded to it. So you can see how these condense down to a more convenient way of drawing these structures. So instead of writing out full Lewis structures, which sometimes can be tedious, we often in organic chemistry will write abbreviated forms or these condensed structural formulas. Let's take methanol. How would this be written as a condensed structural formula? Well, we have a methyl and we have a hydroxyl groups, all right? So we're not showing all the explicit bonds. What we're doing is just showing it as CH3OH, a methyl and a hydroxyl group. What about butane from a butane lighter? All right, that's got 4 carbons. Well, you can see how that would be written, the CH3 with a couple methylenes in there, and then on the other end is another methyl group. So that's the way you can use condensed structural form. So what about when we have double and triple bonds in the structure? This is going to be quite common in a lot of structures. We're going to have carbon-carbon double bonds and carbon-carbon triple bonds. Here's a structure that has a double bond in it. It's called butene, and it has this double bond on the second carbon. That's why it's called the 2-ene here, but it's an alkene type structure. And the question is, how should we handle that? Well, you notice the first structure doesn't explicitly show the double bond. It has a CH and then another CH. I think it would be better, and I would like you to do this, to explicitly show double and triple bonds in the condensed structural formula. So the preferred way, my way to doing that right now, is to write CH3, CH, right here, double bonded to another carbon, so explicit showing the double bond bonded to another methyl group. Here's a molecule called acetonitrile. It's a common solvent in organic chemistry, and it has a CH3 and a carbon triple bond nitrogen. And so the way we want to draw that is, here's a methyl and a carbon showing the triple bond to the nitrogen. And so as long as you have just a single bond, you don't need to show it, but if you have a double or a triple bond, I highly recommend that you show the double and the triple bond explicitly. Here's an aldehyde. This is a function here, right? If you circle that, that's an aldehyde. We're going to learn about all of these functional groups in a later chapter, but that's an aldehyde, and you can see it has a carbon double bond oxygen in that structure there. Here's a ketone. This is a common solvent. You may have heard of acetone before. It has a carbon double bond oxygen with a couple methyl groups. All right, and so that's a ketone. And then here, this is acetic acid. You may know that as the acid that's in vinegar. And so what is a carboxylic acid? The carboxylic acid is a C double bond O and an OH in combination. So we have a methyl, and then we have that carboxyl group showing all of the different bonding of the heteroatoms here. So I'm going to give you some plenty of practice on drawing these structures. You want to be able to convert a Lewis structure into a condensed structural formula and vice versa. Finally, I'm going to illustrate what are called line angle formulas. I like line angle formulas because they're very quick ways of drawing organic structures without showing all the carbon and hydrogen atoms. And especially it's convenient for drawing cyclic structures, and that's shown in this particular table here. But let's start out with hexane. We drew a condensed structure for hexane. This is a normal hexane or N-hexane right here. It's got 6 carbons here, 2 methyls and 4 methylenes. So how would we draw that with a line angle formula? Well, it would be a zigzag, all right? And the way to think about this is this first point right here where my cursor is, that would be on the end of the molecule, and that would represent a methyl group right there. So that methyl group right there is there. And then you have 1, 2, 3, 4 internal carbons here. Those are the methylenes. And then we have another methyl group out here on the very end of the molecule. So that would be a line angle formula for hexane. If we have a double bond, that's easily handled. You just insert a double bond. You put an extra bond in here between these 2 carbons. This one happens to have a double bond between the 2 and the 3 carbons, so they call it 2-ene. And so we have a double bond between the 2 and the 3 carbons on that one. If we have an OH or a hydroxyl group in there, we can easily handle that. You want to make sure, though, that you show the oxygen explicitly on that for a heteroatom. So we could have 6 carbons in a row, and then if we have a hydroxyl group on the 3rd carbon here, you can show that going out to the side for that. Now, I really like line angle formulas for drawing cyclic structures, and they're going to be very convenient for us. You can see a couple, 3 examples that are shown here. What I want to do is illustrate one over here that is much more simple and doesn't have a heteroatom. We'll start out with that one. This is called cyclohexene. All right, it has 1 double bond in a 6-membered ring. It has 1, 2, 3, 4 methylene groups, and then it has the carbon-carbon double bond. Because of that double bond, there's only 1 hydrogen on each of these carbons. And so what you see is a Lewis structure for cyclohexene. How would we convert that into a condensed structural formula? We wouldn't show the explicit carbon-hydrogen bonds, but we would condense that group, and so that's a CH2 or methylene. You can see we have 4 of those, and then instead of showing these bonds here, we just have a CH group and a CH group, so that would be a condensed structural formula, actually drawing the carbons and the hydrogens, but in a condensed way. And then finally, you would have the line angle formula, or line angle structure, which would show just the geometric shape of this thing. This is a hexagon. You can see a 6-membered ring here, and you don't show the carbons or the hydrogen atoms themselves, but the idea of that is that this is implied. This is thought to be a CH2. The structure implies that. There's another CH2. Here's one, and then this one have to have a CH because there's a double bond between those 2 carbons. So that's a line angle structure.